Okay, so here's a mix of Form 5 as well questions and Form 5 chapter 5 question and Form 5 chapter 4. Okay, so this is the SPM question, if I'm not mistaken. This is SPM 2023. Is it? Yeah, it is SPM 2023. Okay, so first, name the type of transistor K. Okay, so remember, a transistor can function as an automatic switch and the thermal thing. Okay, so here is an automatic switch. Okay, so it's, you have to know that this is the base circuit. This is the collector circuit. Okay, this is the base, this is the emitter, and this is the collector. Okay, so when the current is heading towards the emitter, this is an NPN transistor. Okay, so this is an NPN transistor. Transistor NPN. Okay, next question. Okay, explain how the diagram 4 lights up in the dark. Okay, so let's look at the diagram. Okay, you have to understand that when the temperature, this is we're talking about in light intensity. My apologies. So when you're at day, so when you're in the day, you know what? Okay, so when you're in the day, the resistance of the LDR, okay, or the resistance of LDR becomes very low, okay, when you're in the day, because there's high light intensity, so the resistance in LDR becomes low. So when there's low resistance, since this is called the base circuit, the current traveling would be so low. IB, the base current would be so low, and there's even a resistance here, so that when it passes through here, it's even lower, and therefore there's not gonna be any current IB that passes through the transistor. So this means that when there's no base current, then there would be no collector current. I'm not sure what it's called, but there would be no current in the collector current. Yeah, there would be no collector current. So it means that here, which is IC, it would not light up the bulb. So the bulb does not light up in the day. Okay? Whereas when at night, the LDR, it has such a high voltage. So when there's high voltage, this means that sorry. Start with resistance always. Okay, so when there's high resistance in the LDR, the voltage as well will be high. Okay, you have to remember that when resistance is high, voltage is high. So this causes, when the base voltage increases, then there will be base current flowing. Okay, when base voltage increases, base current will be flowing. So base current flowing, but it's still big current, but then the resistance is here, so it becomes slower, but it's still flowing. Okay, so as soon as it masuk the transistor is able to be activated. The transistor will be on. So when the transistor functions, the base current, or the current that's flowing through the transistor, will not increase so much. Okay, so now it's not the base circuit anymore. It's called the collector current. So the collector current will be so large, and then it will be able to light up the bulb. Okay, so if you understand that, we can just put it into words here. Okay, so when the resistance in LDR increases when surrounding is dark, the base voltage increases, the IB flow to switch on the transistor, IC flow to switch on the bulb. Okay. Next, The resistance of light-dependent resistor, LDR, in the dark is 50 kQ. Okay, please look at the unit, okay? Look at the unit. Okay. Based on diagram 4, calculate the voltage across the LDR. So they want us to find the voltage across the LDR. Okay. So they want us to find this voltage across the LDR. Okay. We already have the given voltage here. So what we have to know is that this is equal to V in. And it's just a way I remember. Okay, so then this will be my V out, which is basically the VLDR. Because you need the base circuit, the V out. Because it's a potential divider between this and this. And since this is my V out, the R that I will take as my numerator, okay, dia kata LDR, the resistance is 50 k ohm. So this is 50 k ohm. So V out will be at the same position as this resistance, kan? So based on the formula in our exam module is V out is equal to R2 over R1 plus R2 times V in. Okay, so this is kind of like if you don't really understand, you won't know where to insert the formula. So I remember an easy way is that what I want to calculate will be this, okay, my V out. So I'll use that information, and this, the opposite from it, which is my 50 k ohm, will be my R2, and this, the one other than it, will be my R1. So just use the one information that you want to find, and then the resistance for that information will become your numerator. Like, you guys, hopefully that explains why I'm calculating it like this. So V out is equal to 50. Don't forget it's k ohm, okay? K is 1000. So times 10 cube over 10 times 10 cube plus 50 times 10 cube times with 18. And you get 18 block. You get 15 volt. Okay? Next. You actually, okay, let's say if you say you don't even have to times with 10 cube, I'm only asking you guys to do this so that you don't make a mistake later on in this question, okay? They want us to find the current flowing through LDR. Okay, the current flowing through LDR is this one, right? Is this section. So ignore any other section other than that. So we focus on the base circuit. This over here. Okay. So we already know that VLDR, the voltage is equal to 15. And we know that the resistance here is 50 k ohm. Okay, now we want to find the current. Okay, each of this, the formula is VLDR is equal to IR, kan? The resistance is also from LDR. Okay, so now we want to find the current in LDR. Okay, so VLDR is 15. I is this. Don't put 50, okay? Because this is not in its SI unit. In order to find the correct answer, you need to make sure everything is converted in an SI unit so you don't make a very careless mistake. So take 50 times with 10 cube because it's k ohm. And then you get 0.38. And that is the final answer. Okay. Next. Okay. Mark the direction of the force on the current carrying conductor. Okay, so this is Form 5 Chapter 4. Okay, Form 5 Chapter 4. Okay, so actually I already did this. Okay, so if your power in left-hand's Fleming's left-hand rule, then it should be fine. So just point your index finger to where the north and south is, And then when you see the current is flowing this way, so you point it outwards from you and you get that the force is moving down. So this is the answer. Okay, define catapult field. Okay, this is in your textbook. Catapult field is defined as the resultant magnetic force. Resultant magnetic. Resultant magnetic force when a current carrying conductor. Blah, 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 blah. Wait. Resultant magnetic field. Sorry, guys. Resultant magnetic field. Resultant magnetic field produced by the interaction between the magnetic field from a current carrying conductor and the magnetic field from the permanent magnet. Okay, resultant magnetic field. Okay, then this is just a comparing, so you don't really need to know much. You just compare, and you can get that from the what do you call it? The information given as well. What I want to focus on is, okay, this one is also you can get from the information. What I want to focus on is this question, the potential difference and the force. So basically dalam this question dia tak bagi per force, but then they want us to compare potential difference and the force. But what we need to know is that when the potential difference increases, the speed of rotation of coil increases. So when speed increases, this means that it uses a more force, a higher force in the electromagnetic force and whatever in order to increase the speed of the coil. Okay? So you don't have to think much about that. So when potential difference increases, the force increases. Okay? Okay dah. Okay, I'm gonna ask. Okay, this is what Google says. Why, when potential difference increase, force increase? Because the increase in potential difference does not directly cause an increase in force. Instead, it is the work done by a conservative force that is related to the potential difference when I go blah, blah, blah. Okay, never mind. Okay, how do I explain? Okay, so you guys know the definition for potential difference is the work done. Okay, that work done, okay, imagine that as force. Okay, the work done to move one column of charge from one point to another. So imagine like work done. So basically it wants to push the current to go from one point to another. It needs force, right? So it means that when potential difference increases, force increases. Yeah. Okay, so now the question asks, what happens when the dry cell in diagram 6.2a is replaced with an alternating current power supply with frequency of 50 Hz? What will happen to the rotation of the coil? Give one reason for your answer. Okay, forget the 50 Hz right now. Tengok alternating current power supply. Okay. So what happens when there's a alternating current supply? Okay, so what happens is that this is in one direction kan. When there's an alternating direction, dia akan pergi from left to right, 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 right? So it means that it won't move kan, because if you keep on going left, right, left, right, left, right, you're not going anywhere, you're just vibrating. So basically, let me give you an example. So when you have a first half turn, okay, let's say this is the direct current, so there would be a left side force would be like this and the right side force would be like this kind. So that causes the coil to move, but it would have a direction, it would be clockwise. Tapi let's say 6.2b you nak tukar dia jadi alternating current, then you okay, let's say you get for the next turn. Okay, so let's say this one is left side force. Okay, they go down, this one go up. Okay, this is dia pergi sini, and then it's like dia tukar pula, dia naik atas, dia naik bawah. So it just keeps on going, like it means that it keeps on, the direction keeps on flipping lah. The direction keeps on flipping. So the coil would not really rotate. So instead of like a clockwise force the rows, it would be clockwise, anti-clockwise, clockwise, anti-clockwise every 50 times every second because of the hertz kan. So imagine if you want to push someone, it's supposed to fall, right? But instead, okay, imagine if you want to push someone, the person is supposed to fall, right? But then instead, it's gonna push you back. Oh my god, it looks like it's holding hands. But okay, basically, like, from that, can you vision that it's not gonna move? Like, it's just gonna keep on being like that. So, the answer given is this. You can either say vibrate, or you can either say stationary. And then the direction of force changed. Or you can say the direction of the force changes continuously.